I'm going to lecture with a different toy. It's not that I haven't owned this piece of equipment, but I haven't used it. And so I'm using my Wacom tablet and not my iPad. It's a good idea for students to purchase one of these if you're going to be in virtual learning any more of your life, because it's only like $100. And you can get software like this one. It's called Smart Notebook. You can put your documents in there, and then you can write on it. It's easier than writing with your mouse. I should have done this earlier, just some of the times. All right, let's talk about 8.5. And he's using the word trigonometric form of complex numbers, but in a polar sense. And you have no idea what polar means. So I'm not even going to talk to you about, let me get a pen up here. That color is just, oh, let me see if I change the color of that. Still black. Okay, that's fine. Black works. I'm going to try another color. Let's see. The colors are here. Well, maybe I got to grab it from here then. Depends on form. Yeah, that's what it did. Basically, you're going to recognize it's trigonometric, and you're going to recognize complex numbers. Now we're putting them together, and we're going to do another lesson before we leave on polar equations. But for now, trust me, the name for this stuff is trigonometric or polar form of complex numbers. There's your typical vocabulary. I'll define some of this as I go through. All right, so we have done polar in the past. I mean, polar. We have done complex numbers in the past, is what I meant to tell you. You might recall looking at numbers like the one that's listed right here. Let's see. Yeah, right there you see 2 minus 3i. Is it right? There it goes. 2 minus 3i. And we did some manipulation of that earlier in college algebra. And I may even talked about what it looked like to graph. So it looks like the XY plane, but I want you to realize that this is Y. He has it written up here as Y, and he has this as X. But Z is another value, and you can look at Z as this imaginary axis that comes out at you. Okay, comes out at you. You don't see it. I'm more comfortable with drawing it. I have an eraser, but it's just as easy for me to go erase that writing. A lot of people, when they do their Y and their X, they draw their Z like that. So you can see that it's like the bottom of a box, if you want to look at like it's a corner. So you can kind of visualize 3 dimensions. So we would call this my X and this my Y, and then this would be my, well, for complex numbers, I don't call it Z. I would call it, well, let me just call it Z for now. There's no Y needed for complex numbers. So you could get away with just saying two axes like we do normal. And you could call this your I, and you can call this your X. X stands for your real number part, because remember, with 2 plus or 2 minus 3i, this part here, as you recall, was your real number part. It's real number. This part here was called your imaginary part. Like, where does that come from? Like, you take the square root of a -4, and you got 2i. That's an imaginary number. Okay, it doesn't have a real part. Now, if I said 2 plus or minus the square root of 4i, then you would have 2 plus 2i, and you would also have 2 minus 2i. And we've already done that in the past. So that's your review of complex numbers. And now we're going to graph it. And so if you graph it as a three-dimensional, and the reason that minus 3i is because I don't see, he's using his y-axis. He is using his y-axis as his I, like I did right here. See how I said that this could be your I-axis? So even though he's labeled it y, he's using it as his I. Change color for some good reason here. So when you graph 2, then that was 2 over on the x component. When he graphed negative 3i, then on the y-axis, he goes down 3. And so you pretend this is a three-dimensional thing out in space. So he put his dot out here and pretend that you are graphing a vector from the origin to this sitting in space. Okay. So it's coming out at you, but he's used the y-axis as your I. So even though he called it y, it isn't y's. It's not a real number y. It's his I. And he does say at least it's the imaginary axis. At least he says that. I've not seen it quite like that before, where he said they actually called it y for some reason. All right. To graphic complex numbers such as 2 minus 3i, we modify the coordinate system by calling the horizontal axis that's going to be the real number part. So real, and since it's an axis, we'll say real axis. That's the x-axis, basically. And the vertical axis, which was called the y-axis, we're going to call that the imaginary axis. Imaginary axis. I don't know if I can write better on this. Maybe I can zoom in, make it bigger. I don't know. If I had more room in there, I'd feel comfortable. Let me see if I can. There is a view button. There is a zoom. I don't know how much it'll go up if I say 120. That's even smaller. View, zoom. I'm playing with my new toy, so let me go 200. That's a little better. Let me view, zoom it to, I don't want to go 300, but let's see. Whoa, yeah, that'll work. It'll work. I like it. But then, no, you can't see everything on the side. I'd have to somehow figure out how to scoot this over if I need to. Yeah, well, okay, well, right now I'm going to do this. I can write on it more. The complex numbers can be graphed in units. In this, no, I didn't say that. Graphed in this. Not really sure what he's calling that. Be graphed in this. Well, I think the author was thinking it would be called unique position. As shown in the figure, each complex number A plus B represents a unique, yeah, that's what he used. Unique position vector with the initial point 0, 0, because that's what I even said. I said I started at the origin, then a terminal point. Well, in this picture, let me scroll over. See, in this picture, my terminal point was here. It's going to be whatever I can draw that. That would be an A. Some A, it's a real number. Why did my color change on me? I don't know why. Let me change. I like blue. don't know why it changed on A. And then I can't write that small. That's the problem. And I don't want to go, I can't get bigger. I'll just write it underneath that. That way you can see A plus BI. I'll go A plus or minus. But if you say plus, you can add a negative number, BI. So that's, it's that he probably put this down here in the notes. That's going to be your terminal point. So I'll write, it's going to be a point where it's A is your real part, that's your X. And then we say B is your imaginary number part, and we put an I on it to tell you that it was on the imaginary axis. The geometric representation is the reason that A plus BI is called the, let's go on, the geometric representation is the reason. I don't know what he means by that. It's called the, I don't know the blank. If you figure out the blank, you let me know, of a complex number. Vector form, maybe. I could go with that, but I don't know what the author was thinking. Okay, I'm not gonna. I'll put the word vector form on because he is drawing it as a vector. So that would be, I'm going to put vector over here. And the geometry does show that it's a vector coming out. Form. That's bad F. Gotta get used to writing this. Well, it's hard to write on these note pages. It's easier to write on blank paper. Okay, now rectangular form is also known as, I'm not sure what he wants there. I'm going to move on. Okay, graphically, the sum of two complex numbers is represented by, so now I know I don't like it being so large. The vector that is the, okay, we did it in geometry, the form. It was the resultant. When you add two vectors, so I called it vector form for a reason. So we called it, when we added two vectors, we called it the resultant. That fits pretty well. When you add two complex numbers, since they are vectors, when you graph them, that we could treat the sum of two complex numbers as a resultant. Did I miss a T? Resultant of the vectors corresponding to the two numbers. Now, expressing the sum of complex numbers. So we're going to take two complex numbers. Now, you already know what it is. Watch. In the old days, when you were little, we had 6 minus 2i and negative 4 minus 3i. And we knew that we had to add. We were adding them. Put a plus in there. So we added the real parts and got 6 minus 4 was 2. Then we added the imaginary parts, and they're both negative, so that's plus minus 5i. So that's just the algebra, okay? But if I go to the graph and I treat them as vectors, what was my first vector? See, I already almost lost where it was. What were my vectors? You're not here to tell me. It was 6 minus 2i. And so we're going to write that down again, closer over here. I'm adding 6 minus 2i, and I'm adding a negative 4 minus 3i. So in the drawing, we're going to treat the y-axis as the I, and I'm going to treat the, so whenever you see something coming up, it's actually a bi. So some number times I. And then on the x, that's my a component. So when I graph 6 minus 2i positive 6 down 2 is going to be where I put my dot. And then I'm going to, from 0, 0, I'm going to draw my vector out there. Now, if you choose to put the arrow, if you remember what I go all the way down, 1, 2, well, actually, I'm just a terrible artist. Let me move that dot a little better dot. Okay, 6, it's my vision too. There, can I get there, hit that right there? Okay, that's good enough. So there's my origin. And you can put an arrow if you wish, but we know it went to 6 minus 2i. And then, I'm going to draw it here so I can, 6 minus 2i. The other one was minus 4, so the x is negative 4, and I'm going down 3i. 1, 2, 3i, if I can get exactly there. So that vector, out in space, coming out, and bam, it hits it. Now, what do we know about resultant? We know the picture. I'm just going to do it. I'm going to do it just not any math. I'm just going to go and change my pen to be black. And how did we do a resultant? We took each parallel side and we created a picture. I'm doing it with a rough, just a graph to show you that that's parallel to that. And then I'll change the color again. Then the blue, it's parallel going this way. Now I made this up, so it's probably off. I didn't even count. And the resultant would be the colors. Maybe I can do yellow. From the origin, a diagonal, that would be my resultant. Okay? That would be my resultant. I'll put an R there. Now, theoretically, if I was a perfect artist, that vector in yellow should be, change my color back, since the sum was 6 minus 4 is 2 minus 5i, then theoretically I should be able to go 2 to the right, down 5. 1, 2, 3, 4, 5. Not too bad. Not too bad. That means that vector, which is the resultant, and I called it R, is 2 minus 5i. So geometrically, it lines up to what we know how to add to complex numbers. Okay, let me go to the next page. Now, what do I know? What, did I miss something? Seems like I missed a problem or something. No, there's no more problem. Okay. All right. I'm going to unzoom this so I can read better. When I write, I don't mind zooming in. You zoom, just go to that's 100. Oh, that's too small for me. You zoom. What was the normal page then? 125, 150? Yeah, probably 150. Okay. So we've learned in the past that if we were looking at a triangle coming out of the xy plane, and this has an x value, and this has a y value, and then we have our little tiny theta in here, theta. We've learned that that's the right triangle. I'll put my little right triangle. I should have made it bigger. That's a right triangle there. And we've learned that sine of theta was always equal to x over the hypotenuse, which if this is a unit circle, that was r. So if I solve it for x, and we did this in the other lesson, x is r sine of theta. And using the same information, wait, I'm sorry, yeah, r sine of theta. It wasn't x. It was x is r sine of theta. No, it's not. Wish I could rewind. Rewind all my talking. Opposite. Hello, Cartwright. Opposite. Sine of theta was equal to the opposite over r. There, that's better. R equals, well, r sine of theta equals y. And then we have that would be this one right here. And then we have the cosine is adjacent, that's the adjacent over the hypotenuse. So it turns out that r, or not r, what am I doing r? When I did this one here. I'm supposed to solve it for y. Y was r sine of theta. Then if we do the cosine one, we get x is r cosine of theta. So you'll want to memorize these. You did them in the other lesson. And how can we use them? Well, if you want to find that radius right here, that distance, you could call that a vector coming out. How long is it? What's its magnitude? Think of it as a triangle. Pythagorean theorem, x squared plus y squared is r squared. Take the square root, both sides, and you got r equals the square root of x squared plus y squared. So there's this formula from the other day, and plus it's just some common knowledge in this formula. Now we have the r, which we've used that before. You have used that before. But what about the angle theta that is in here? What do I know about angle theta? Well, I know about theta is that using the same angle, that the tangent of theta has to be opposite over hypotenuse, y over x. So as long as x isn't 0, so there's that formula. So we have a lot of power we have in our hands to manipulate our vectors. All right, now how is this related to the trigonometric or polar form? What we do is this: the blank, blank, or blank. Okay, well, he's calling it the trigonometric form, and it's real small, so let's see if I can do it. Trig. I can't write straight because I'm writing on I can't see it on my these drawing tablets are made for artists, and they're looking at the screen, and so they're already good at art. So I'm looking at the screen, drawing on my desk. The trigonometric form, or he's calling it polar form. Polar form. And I'll write that word here. Of a complex number, since there's two pieces in a vector. How can I put them together? So that's what he's done. He's put them together. But interesting thing about my y value, remember my y has to do with my bi. That's my complex part. The y part is. The x is the real part. So here's the x is the real part. And here is my plus my bi. And b is the imaginary part. So you see he has to put the x part goes with cosine of theta. So that's why you see cosine of theta inside, cosine of theta, that's my x. And that's remember my complex is a plus or minus bi. So plus or minus my b, I has to come from y equals r sine of theta. So if I put the r there, and I put the r there, r sine of theta, he factors the r out. See that? So if you factor the r out, and I know writing in where I need my room. But the good news about this particular program, I can hit, well, if I move this bar out of the way, you don't see the bar, but I have a bar that's in the way. I can hit for extra spot, and I can say that R, quit writing on me, R cosine, I forgot my, what was my cosine theta, right? That's my X, that's my A, plus or minus my BI. So it's sine of theta. And don't forget, there has to be an I with it. So we put the I on this side because it'll mix up with the argument if you put it there. So factored out the R, and that is called a trigonometric form. There's a shortcut for that. I think he's going to tell me up there. Let's see, is it up there somewhere? Yeah, he says that. The expression cosine plus R sine of theta is sometimes abbreviated as the word cis. C-I-S of theta. Because that means I don't have to write this whole thing out. I can just write R cis of theta. But I still need to remember what cis means. Okay. Like if I'm looking at this right here, I'm just going to rewrite this. I don't want to write all of this. So I could just write 2 cis of 300 degrees. Because then that means cosine and the sine. And also the I is embedded in this part in that part right here. So when I see that, then I have to know that means 2 times the cosine of 300 degrees. And since it's, there's no reason for me to believe that it could be a plus negative, but plus I sine of 300 degrees. That's how you would write it. Wait a minute, that's what he wanted me to do. I just did it. Well, no, he wants it in rectangular. Okay, I didn't write it in rectangular. What form am I written in? This is not rectangular. This is polar form or trigonometric form. Whether you write it like this or whether you write it like this, it's still polar form. He wants rectangular. When you see rectangular, that means he wants it to be back with only X's and Y's. You got to convert that. Well, if you look, remember what we said up here. We said that X is R cosine of theta. So you know cosine of theta is cosine of 300. So why don't we just write, let's see, do I need X's and Y's? Not really. Let's see, X equals to 2 cosine of 300 degrees. Y is equal to 2 sine of 300 degrees. When we get done, we should have an ordered pair. Okay, so cosine of 300, I think he uses his calculator. He cheated. But 300, change color so you can see what I'm doing here. 90, 180, 270, 300 out here. That gives me 60 degrees left. That's my reference angle. And I'm in quadrant 4. Cosine is still positive in quadrant 4. So it's going to be X is 2 times the cosine of a 60. If you need to do the scratch work and you're thinking about what are the measurements, if this is a right angle, right here, right angle, and this angle is 60. Remember that this would have to be a 1, and this would have to be a 2, and that's a square root of 3. So the cosine of 60, cosine is adjacent over hypotenuse, that's 1/2. So it's 2 times 1/2. And the sine of 60 would be opposite over hypotenuse. So this would give me y equals to 2 times the square root of 3 over 2. And the 2's cancel. So I have an ordered pair here, 1, comma, square root of 3. That's where that point is. 1 square root of 3. And which time do I got? Because I have a class coming. And so I'm going to have to call this part 1, and I'll have to create the second video, part 2, and then I'll put them, I'll give you both links for the, maybe I can merge them. Maybe I can learn how to combine 2 videos. We're not done with this yet, but, oh, I messed up too because sine is negative here. I better put my negative. Got to always ask yourself, what quadrant am I in? So it had to be negative. This had to be negative. So I should have put my negative right up at the beginning, and I might not have forgot it. Okay. We're not done with this problem yet, but I'll finish it up. So let me get back into my, unshare my screen. And I'll have to stop this, and I'll do a second one after.